Question 2 is about statistical inference and error probability. So part A is we perform a statistical test with a p-value cutoff of 3% or 0.03. So the question's asking, if the model is good, then the chance the test will conclude the data are consistent with the model is what? So let's just break down what this means. So if the model is good, means if the null hypothesis is correct, because remember we always simulate under the model given by the null. So if the null is correct, then the chance that the test will conclude that the null is correct, meaning the chance that it will correctly identify a correct null hypothesis is what? So the way we solve this is by using the error probability formula, which is basically the probability of falsely rejecting a null, we'll just call it error, is actually just the p-value cutoff. The reason why is because the cutoff we set is completely arbitrary, and as you've probably seen in many different examples, even under the null hypothesis, it is still possible for data to be more extreme than you're observed, even when you assume the null hypothesis is true. So the probability of an error here is 3%, or 0.03, meaning that the probability of no error is going to be 1 minus 0.03, which is 0.97, so about 97%. Okay, part B. So we do a simulation where we draw a histogram of 10,000 coin tosses, and we see how many times we get heads in 10 tosses. So our histogram looks like this. So now, if we simulate 100,000 times instead of 10,000, what will the histogram look like? So the answer is histogram C, which is the one that is basically the exact same as our example here. So this is due to the law of averages, which means that over a large enough sample size, the empirical histogram and what it theoretically should look like are going to be the same. And in a similar vein, when we have two adequately large sample sizes, which 10,000 and 100,000 are, then we'll also get a very similar looking histogram. So C is the correct answer. Okay, let's look at part C. So when the following code is run, the expression in the last line evaluates to a number that's equal to one of the choices. Okay, so let's figure out what this code does. So first we see counter equals 0, which indicates that we're going to be counting something. Then for I in np.arrange 100,000. So that's a for loop, indicating we're repeating a certain thing over and over again, and we're doing it 100,000 times. Okay, so roles equals np.randomChoice of 1, 7, 10. And so what that means is that we are drawing 10 times from an array with the numbers 1 through 6 in it, which is basically like a 6-sided die. And that's why it's called rolls, because we're rolling a 6-sided die 10 times. So then it's if np.countNon0 of rolls greater than 4 is equal to 0, counter equals counter plus 1. So what this line here is saying is what we're counting is in those 10 dice rolls, what's the probability, or how many times out of 100,000 do we get 0, 5s, and 6s? So the best way to calculate this is to just figure out the theoretical probability. So if we have 10 dice, what's the probability that we get 0, 5s, and 6s? So we can break this down into a simpler problem, and that problem is in one dice roll, what's the chance of no 5 and 6? And that is going to be 2 out of 3, because if you don't want to get a 5 or a 6, you need to get a 1, 2, 3, or 4, which are 4 out of 6, or 2/3 of the outcomes. But we need this to happen all 10 times, because in 0 dice, see it says, or in 10 dice, it needs to happen 0 times. So we need to take this to the 10th power, because all the dice need to be a 1, 2, 3, or 4. And when we convert this into Python code, we get this answer right here, because the 2 multiplication signs indicate we're taking an exponent.